invariant reactions in the binary phase, and the aluminum oxide and chromium oxide equilibrium diagrams, binary F-former systems. So further we will go with how this amount of liquid phase can be calculated. So here if you take OMP line, so with respect to center where the balance is happening between the liquidus and solidus line, so amount of solid phase at M we can calculate, that is OM by OP into 100. If we calculate, you will be able to get 30.95%. So 30.95% is the solid phase. Amount of liquid phase at M is MP by OP into 100. If you find out the difference of the value, then you will be able to get 69%. If you add both the liquid plus solid phase, then it must be 100%. So like this, you will be able to calculate the solid and liquid phase. So further important phase diagram if you take, that is the copper and the gold. When we take the phase diagram happens initially at less temperature, there won't be much variation. At 400 degree we can expect the variation to be present. So here equilibrium happens at close to 800 degree. So further we can expect the solidus and liquidus line to be present. So alpha and beta means the Eutectoid phase is present below the lower limit. So as the percentage of composition varies of copper and silver, we can expect at 71.9% the of copper, we can expect the equilibrium state to be present, and with silver we can have around 20 to 25%. So here beta phase is present. So solidus and liquidus line is established. Same if you take with the lead and the tin, the phase diagram varies. So the equilibrium here it is coming at the earlier temperature, that is close to 200 degrees centigrade. So above that we can expect the solidus line and the liquidus line. So invariant binary reactions, it is declared there with gamma and beta, alpha and L. So like this, when we take with alpha plus beta, it gives eutectic output. Alpha plus L, it is the peritectoid output. So like this, different output can be obtained by considering phase diagrams. So further, if you take cadmium and bismuth, here you can see liquid below the equilibrium, bismuth and eutectic phase is present, cadmium plus eutectic phase is present. Above point E, liquid plus bismuth, liquid plus cadmium is present. Above that, it will be in the liquid state. Both bismuth and cadmium completely soluble in each other, so they will be able to dissolve above the liquid state. So the crystal structure of different phase transformations that is happening, it is exhibited in the graph. So further, iron carbon equilibrium diagram, it is iron carbon means iron plus iron carbide, it is combined to check out the phase diagram. So here you can see the iron and iron carbon equilibrium diagram. So initially here you can expect at the two phases the transformation. So at the iron, here you can see the phase transformation happens at two phases. So one is at 700 degree, another one is at 1100 degree centigrade, 1147, 727 degree phase transformation happens. So at the higher temperature, that is at 1538 and 1492, so there will be a once again phase change. So here you have to observe the phase changes, what all it happens. Early it will be cementite, further with gamma plus iron carbide. So like this the phase transformation happens as it is indicated in the iron carbide phase diagram. So here the microstructure of Eutectoid is showing perlite when it is magnified 1000 times with the help of scanning electron microscope. Here you can see how the bonding happens and the structure of iron and iron carbide. It is shown in the perlite. White caster on it magnified 650 times. White regions are cemented, dark regions are unsolved, unresolved perlite which is present in the iron carbide equilibrium diagram. So further we will discuss what is diffusion. Diffusion is migration of atom from their original lattice sites in a crystal structure to other sites. It is known as diffusion. So fixed law of diffusion it is applied. Under steady state flow, number of atoms per unit area of diffusion per unit time, it is equal to the distance between the planes in the direction of flow, that is minus d dc by dx. So this graph it indicates that how the diffusion happens, that is difference between C2 and C1 divided by x2 minus of x1 into minus of d, where dc by dx is the concentration gradient. So by this you'll be able to apply the fixed law and find out the diffusion of atoms. So what is diffusivity or coefficient of diffusion? It is dependent on the amount of substance diffusing in unit type across unit area through unit concentration gradient, and its unit is meter square per second. The coefficient of diffusion of various material vary with crystal structure and temperature. What is the role of imperfections in diffusion? So atoms can also diffuse along boundaries, interfaces and surfaces in the material. Atom diffuses quickly in the grain boundary. So wherever grain boundary is present, atoms will get diffused easily. The atomic packaging is disordered, less dense in the grain boundary. Because atoms can more easily squeeze their way through the ground boundary, activation is very slow. Surface diffusion is easier still because there is even less constraint on the diffusing atoms at the surface. Diffusion of atoms along grain boundaries, it is faster than volume diffusion because atoms are less closely packed in the grain boundaries. Diffusion of small atoms from one interstitial position to another in the crystal structure. Diffusion of atoms when atoms leave regular lattice position to fill a vacancy in the crystal. This process creates a new vacancy and the process continues. In volume diffusion, diffusion of atoms through the interior of grains is possible.